Hello, and a very warm welcome to everyone joining us today for Select Science webinar titled Get the Full Scoop on Your ADC from Microliters. My name is Jemima Arnold, and I'll be moderating today's presentation. I'm delighted to be joined by our guest speaker, Dr. Andre Muella, Marketing Manager for Biologic Solutions at Unchained Labs. This webinar will discuss the problems of working with ADCs and how Unchained Labs is providing solutions. Andre will explain how to use Unchained Labs tools to determine the concentration, labeling, stability, and viscosity data of a monoclonal antibody. Following the presentation, we will have time for a short question and answer session. And if you have any questions throughout the webinar, please feel free to submit these in the box to the right of your screen. Without further delay, I'd like to hand over to our speaker, Andre, and I'd like to thank them again for presenting for us today.
Hello and welcome to my webinar. My name is Andre. I work in biologics marketing here at Unchained, and today I want to show you how you can use our solutions to get the full scoop on your ADC from just microliters of sample. To get the dessert you really crave, you can't just use one ingredient at a time. Dragon fruit sorbet is nice, but you really need a lot of deliciousness to work together for the perfect dessert. That's the same when talking about analytical instrumentation. You need a full panel to work together to deliver a more complete story of what's up with your biologic. This is especially valid in the case of ADCs, which are really hard to work with. You can maybe consider them the sea salt pretzel bits ice cream of the biologics world. They are tricky to work with and need to be dealt with really carefully. This schematic represents the analyte I used to collect the data I am showing today. It's a recombinant human IgG1 that was conjugated with dancil LC-SMCC through cysteine residues. The mass of that tag is about 670 Daltons. This ADC mimic is commercially available. Everyone who has worked with ADCs knows that while they are really mostly monoclonal antibodies, they are really much trickier to work with. They are never available in sufficient amounts for all the tests, and they also tend to be sticky and like aggregating. The solutions I want to show you today help with characterizing ADCs. They are fast and they need only small amounts of sample. They are designed and built for biologics. Let's first take a look at the age-old questions of how big, how much, how good. How do you go about measuring the quantity and the quality of your ADC? Our solution to this is an SBS plate with microfluidic circuits. You drop 2 microliters of sample into your input well. This then wicks into the microfluidics reservoir and is measured in 2 diamond-shaped cuvettes. Why are we using 2 cuvettes? Well, 2 path lengths improve our dynamic range, and most of the time you can measure any sample without the need to diluting it, which really means one less thing to worry about in your day. These circuits come, as I mentioned, in a 96 well SBS format plate. In those 2 microcuvettes, we can then determine the UV-Vis spectrum to find out about the concentration of our analyte. In this example, we are of course looking at a protein, as signified by the high 280 nanometer absorption and the lower one at 260. In addition to the UV-Vis signal, we can also look at DLS, the dynamic light scattering. This yields information about the hydrodynamic size and also the heterogeneity of our sample. Our protein here is about 10 nanometers in diameter, so it's quite possibly an IgG-type molecule. The size distribution we're observing is nicely sharp and narrow, suggesting a homogeneous prep without any aggregates. The measurements in these plates are fast. 96 UV-Vis reads will take about 10 minutes, and when you add DLS, it will still be under an hour for 96 samples. Of course, you can dial in the acquisition time and the number of acquisitions for DLS as you like. As I mentioned, I will show data for a recombinant IgG after conjugation of a dancil moiety. In this graphic, we see the UV-vis spectra of the monoclonal antibody alone, this is in green, and then the ADC in blue. Good thing here is that the dense moiety absorbs around 335 nanometers. So in case of the ADC, we can quantitate both the protein and also the included drug mimic. This is possible as we have an application called Homebrew that is able to deconvolute the absorption spectra. As we know the path lengths and the Lambert-Behr law, we have all we need for this quantitation. So what does the data look like? Here's the results, the monoclonal antibody and the ADC concentrations based on quadruplicate measurements. So you see very high precision here. And when we look at the DLS signal that we have as well, we see that the ADC is a little bit bigger in hydrodynamic diameter compared with the corresponding monoclonal antibody. The Dancel drug mimic is about 16 angstrom, including the linker end to end. So a contribution to the size of the overall ADC makes sense. The polydispersity indices that we determine here, the blue dots, graphed on the right y-axis, for both monoclonal antibody and the ADC are well below 0.1, is two nicely monodisperse preparations. When we're looking at the results of the Homebrew deconvolution, the drug-antibody ratio we're determining is 4.17. This matches the certificate of analysis provided by the supplier of the ADC really well. This was based on MS and came out to be 4.2. Again, we determine 4.17. All these results are from a total of 8 measurements, and including the DLS, it took under 5 minutes to set up, to record, and to analyze this experiment. Let's now switch gears a little and consider stability of our ADC. As stability of a biologic tends to depend in no small degree on the formulation it is in, we need a good way to buffer exchange our analyte. So how do we do that? How do we exchange the buffer our ADC is in? Common ways to exchanging buffer are dilution. You just add the buffer that you want to go into to a preparation, but that also, of course, means a decrease of concentration. You can use a centrifuge and a membrane-based diafiltration step, but that's highly manual, and plus it bears a high risk of a loss of sample due to membrane crowding and aggregation, or to breaking of the membrane and the sample just running through. You can also dialyze your sample, but that tends to take a long time, take a lot of buffer, and also the loss of sample, the risk of loss of sample is real. All of these steps, dilution, centrifugation, dialysis, are quite painful and quite labor intensive. Our solution is different. It uses a disposable cartridge, here's the comic of it, with a membrane at the bottom. You transfer your sample into this cartridge, you measure the volume, then we apply positive pressure to start our exchange cycle. We measure the volume again, and the system automatically refills buffer and cycles through these steps until the degree of buffer, the desired degree of buffer exchange has been reached. You can naturally, at the end of it, also concentrate your sample further. So all in all, this is an adaptive filtration cycle, adaptive because it measures the volumes and adds buffer as required. We have individual volume tracking for each of the samples we're processing, and the pressure levels that we're applying, the positive pressures we're applying, are programmable. You might think this is just like using a centrifuge, but in contrast to dead-end ultrafiltration, we are avoiding the risks of crowding. So in a centrifugal filter device, you press the sample against the membrane. So there's membrane crowding that can lead to adsorption, it can lead to clogging, it can also lead to precipitation of your sample. We gently mix the sample while the pressure is applied. It's shaken, and that shaking program is of course programmable based on your analyte, and this continuous motion of the sample prevents clogging and leads to a faster, more gentle exchange. Here is what it looks like practically. In the device, in the instrument, we have a rack here with the buffers that can be our sample that we want to concentrate, or it can be the buffers we want to exchange into. The sample of the buffer exchange chamber is here. So this is a door that would close, and then the pressure is applied. Here you see 8 cartridges that are used to hold the sample. Here is a robotic arm with a pipette to fill buffer into those cartridges, and then here, hidden inside the shroud, is the ultrasonic volume sensor. We also have, of course, tip racks. So we need more tips to exchange the buffer. This method really has a premium recovery. So for the 3 applications we have, buffer exchange with following concentration, and also reduced sample volume, we have recovery rates that are above 95% in all cases. The system can take up to 8 samples per run. It's a single sample consumable, so no worry about carrying anything over. You can work with volumes between 0.5 milliliter and 8 milliliters, and if you use the reduced sample volume application, you can go down from 384 milliliters. I teased stability. Before talking about stability, one more thing I wanted to mention is viscosity. When we're talking about different formulations for an analyte, we of course also want to know about the viscosity of the different systems. Viscosity is an important puzzle piece also to assess colloidal stability. For colloidal stability, you might look at diffusion interaction parameter, Kd. You might look at the second virial coefficient, B22, but you can also use viscosity for that. Viscosity is also important for considerations of administration of the drug substance. Most viscometers are slow, need a lot of material, and also a lot of manual or researcher involvement. Here's how we measure viscosity. In this example, we're looking at water, a 2 centipoise viscosity standard, and a 10 centipoise standard. And then we repeat this twice more. So water, 2 centipoise, 10 centipoise, water, 2, 10, and then water again. You can see how the meniscus, how the sample is progressing in this channel, and how the software tracks the leading edge of the sample. Now, how do we get from this to a viscosity? Well, what we were just looking at showed a bun. Each of these buns can run between 1 and 10 samples at a time. The channels you don't use in the experiment now, you can keep for later, of course. You add 35 microliters of sample into an input well, and then you apply pressure. So let's take a look here at the schematic. You apply pressure, and that presses the sample through the microfluidic channel. That has 2 parts, a narrow part, call that the resistance channel, and a wider part that we call the measurement channel. The camera follows the liquid front in the measurement channel, and then as we know the applied pressure, we know the volumetric flow from the camera measurement, we know the geometry of the channel, we can calculate the viscosity. With this, gone are the days of filling syringes or cleaning expensive chips that are prone to clogging. These buns are disposable. You use a channel once, and after you use all 10 of them, you take a fresh one. Now you can gather as much viscosity data as you like. The speed and throughput make it easier than ever to gather viscosity anytime you make a change to your protein's concentration, or the formulation in general. Here's 10 samples run in parallel. This is an IgG formulated in PBS in 10 different concentrations, and we look at averages with error bars with standard deviations shown here, and you can see how precise the reading is. We're going from left to right with increasing concentrations. We can see how it starts increasing more steeply at past 35 milligrams per milliliter. So viscosity increases as the concentration increases, as expected. This statistical analysis, so the standard deviations, come from the ability to run multiple shear rates in a single run. So every data point we look at in the viscosity versus concentration plot here comes from a sweep over multiple shear rates. These are averaged, leading to the results shown here. So because we are sweeping over different shear rates, we can assess how the sample is flowing and if it is Newtonian or not. A Newtonian sample will show a horizontal line, no influence of the shear rate on viscosity, but they could also see something that is shear thinning when the viscosity decreases, or shear thickening when the viscosity increases. So with a measurement like this, you can get the viscosity, get the statistical analysis, and you can also talk about the Newtonian behavior. Getting back to the monoclonal antibody we used in our study, here we look at it in 3 different formulations. I'll talk about these a little bit more later, but essentially used a citrate buffer, pH 4, citrate buffer pH 4 with 150 millimolar sodium chloride and PBS. And we see here that the viscosities are pretty much alike. There's not much difference between them. What I really want to show you here is that we were able to gather reliable data for these 3 samples in under 2 minutes. Actually, the longest step in the experiment is waiting 20 seconds for the sample to thermally equilibrate. I did mention the relevance of viscosity for injectability. When we compare viscosity of an analyte at different concentrations, we'll be able to assess what concentration of our biologic are injectable and which are beyond the limit. That is generally considered to be 25 centipoise, and so for this monoclonal antibody in this buffer, 200 milligram per milliliter are in the range of where the cutoff is. This viscosity as a function of concentration data should of course also be gathered at different temperatures to see what happens with an injectable sample when everything is cooled down, for example for storage. Here we're looking at IgG viscosities measured in triplicate at 4 different temperatures, 10 degrees, 15 degrees, 20 and 25 degrees. And we're looking at a range of concentrations from 0 to 75 milligrams per milliliter. Each temperature here is one discrete experiment, so we are looking at 4 individual experiments set up with 15 total samples each. I want to point out that even at the coldest, highest concentration data point here, we still have a really high or really low percent CV of 0.8%. On other viscometers that are available these days, this is going to be a massive project to collect all of these data points. But here with our solution, we are done within hours. Now, let's, for the remainder of the talk, finally focus on stability of our ADC. How stable is it? How stable is it in a thermal gradient, or how stable is it over a longer period of time? We can also tackle this question from the other end. Is there something we can do? Is there a formulation we can improve on to keep our ADC happier longer? For ADCs, as for all other proteins, there are 2 phenomena we need to look out for when we talk about stability. There is, of course, an equilibrium between the natively folded state and the unfolded state of the protein. We call this the conformational stability. In a thermal ramp, adding more heat energy will make the protein unfold. To make things more complicated, both the natively folded protein and the unfolded one can also aggregate. So we need to keep the colloidal stability, the aggregation, in mind as well. Only by looking at conformational and colloidal stability at the same time, we will be able to assess stability and refine the conditions our ADC is in. Now, these 2 phenomena, conformational and colloidal stability, are probed using 2 distinct methods. Unfolding, or conformational stability, is determined by monitoring the protein's fluorescence. What we are looking at is really the aromatic amino acid residues that are normally buried on the inside of the protein, where it's non-polar environments. But then as the protein unfolds, they will get in contact with the hostile, if you want, aqueous environment, and that leads to a change of their fluorescence behavior. The fluorescence will decrease and shift in wavelengths usually. So by following the fluorescence signal over time or over temperature gradient, we can assess what the how the unfolding progresses. If we want to look at colloidal stability or aggregation, we will monitor the increase of the static light scattering signal to see when the sample aggregates. SLS is a function of molar mass, and so as the aggregate forms, that signal is going to increase. If both of these capabilities are combined in one experiment, these behaviors can be tested simultaneously. Before I'm going to show you data recorded for fluorescence and SLS in a thermal ramp. Let's just do a quick QC check of our ADC after our buffer exchanges. The buffers, as I mentioned in the part on viscosity, are citrate, pH 4 in green, citrate with sodium chloride in blue, 150 millimolar here, and then also PPS in red. The QC check before a longer experiment is done with DLS, so that focuses on the diffusive properties of the analyte, and the results yielded are the diameter, see that here on the x-axis of the analyte, together with the polydispersity index as a measure of homogeneity. For our ADC in the 3 formulations we're looking at today, we see that at 15 degrees, the size is in the range of 11 nanometers, so very much as expected for an ADC. The citrate with sodium chloride condition in blue has a higher degree of polydispersity. Let's keep that in mind for now. Now, what can we learn from a thermal ramp? This is what the results of a thermal ramp stability test look like. Our ADC in citrate buffer here shown in green. The fluorescent data is on the left y-axis and is the bold line. And as the temperature increases, we can see how the fluorescence shifts to longer wavelengths. We're looking at the BCM, the barycentric mean. This shift to longer wavelengths is something we call a redshift, because longer wavelengths are redder. If we're looking at, or we're finding, the software finds the inflection point, that is the melting point Tm, and for our ADC, that is 57.6 degrees Celsius in this pH 4 citrate buffer. The static light scattering signal is on the right y-axis, and it's a dotted line, and we look at when the signal jumps over a certain threshold and define the temperature of aggregation, Tag. In this example, this is 64.7 degrees. Is there anything we can do to optimize the stability of this ADC? Is there anything we can do to push these parameters higher? Well, one thing people oftentimes use as a first influencer of stability is varying the salt concentration. So if we exchange our buffer, or if we exchange our sample, our ADC, into a sodium chloride containing citrate buffer, we see actually that the melting temperature decreases by 1 degree, the aggregation temperature decreases by almost 6 degrees. So this is not exactly what we would call a stabilization. If we desalt our, or if we exchange our buffer from citrate buffer, if we exchange our ADC from citrate buffer, to PPS, we see a massive increase in Tm, so about 12 degrees higher now. Aggregation temperature is around about the same, so that remains stable, but this increase in melting temperature is a massive increase in stability. This ADC seems to like PPS. Recording the DLS signal after the thermal ramp yields us an orthogonal confirmation of sample aggregation. Here in this case, the citrate condition in green shows some sample remaining at 11 nanometers, but in all 3 conditions, so citrate, PBS, and citrate with sodium chloride, we have a good amount of aggregates visible here, and some of these are really large, beyond the 1 micrometer size range. Thermal ramps, like we just looked at, are quick and give you a lot of information about your ADC in about 2 hours. However, another important piece of the stability puzzle comes from accelerated stability testing. So in other words, long-term isothermal incubations. The data I want to show you in the next couple of slides are from a series of isothermals that were recorded over the span of a work week. So see it as a scouting study for even longer incubations. We incubated our ADC at a constant temperature, monitored fluorescence, static and dynamic light scattering, then increased the temperature and repeated. Looking at the static light scattering signal over time, over the course of the experiment, it's pretty clear that citrate and sodium chloride is the one that shows the fastest increase of the static light scattering signal at the lowest temperatures. So here's 37, 42, 47, 55, and 62. And for the blue citrate and sodium chloride, we can see the fastest increase at the lowest temperatures, namely 37 and 42. In citrate buffer in green, this increase of the SLS signal is significantly slower, even at 47 degrees. It's not as high as this one would have been. And PBS is the most stable. We see the biggest increase at 62 degrees only. What I have plotted here is the fold increase of the static light scattering signal. We can, of course, also graph this as absolute SLS values. Our software fits phased mean lifetime exponential decays to this isothermal raw data and yields rate constants, shown 2 here, that allow the numerical comparison of different conditions or different candidates. All in all, the results of this isothermal study confirm what we saw in the thermal ramps. The ADC is most stable in PBS. What I find noteworthy here, though, is that in the citrate and sodium chloride condition, the aggregation temperature was 59 degrees, but we already see significant aggregation at 37 and 42, and actually aggregation peaks after storing the sample at 47 degrees for a couple of hours. The citrate condition had a T-ag of 65 degrees Celsius, but sometime at 55 already maxes out the SLS increase. What about this maximum followed by decrease we see in all 3 conditions? Static light scattering is a product of molar mass and concentration, so a decay of the SLS signal could be due to deaggregation or could be due to precipitation. If we look at the DLS data that we recorded for these experiments at the same time as recording the SLS, there is absolutely no indication of smaller sizes. The aggregates remain large. For simplicity, we're looking at only the DLS data from the incubation stage during which the SLS signal peaked. So for citrate, it's 55 degrees. For citrate and sodium chloride, it's only 47 we're looking at, and we're looking at PBS only for 62. The arrows here mark the time points at which the SLS signal had its peak. And as we see, going beyond that on the time axis, the sizes of the aggregates determined by DLS do not decrease. That means the SLS signal loss is not due to deaggregation. It must be due to sample precipitation. So in summary, monitoring the static light scattering and the dynamic light scattering signal in the accelerated storage test adds important insights to what we know from the ramp. What I want to point out here is also that DLS data is susceptible to number fluctuations, especially when you're following aggregation. So what we're looking at here is not the DLS raw data, but a fit to it. All in all, I think I was able to show you examples today of how you can use Unchained Labs solutions to characterize your ADC. First, we looked at Stunner, our quantitation and sizing tool to determine your concentration, your size, your polydispersity. We have the Homebrew app in Stunner that allows you to determine drug-antibody ratios and can run up to 96 samples at a time, 2 microliters of sample required. Unagi is the tool for buffer exchange I introduced. You can use it to exchange buffers to concentrate samples. It uses a gentle ultrafiltration diafiltration. It's fully automated, and you have full control over the process. Even sends you text messages when your process is finished. You can go down from, you can concentrate 384 milliliters down to half a milliliter. Honeybun is our solution for viscosity, run up to 10 samples in under 3 minutes. You can deal with Newtonian and non-Newtonian behaviors, no need for cleaning, and the setup is so easy you wouldn't believe it. Uncle, that is the tool that we used for stability, is our melting and aggregation, our all-in-one stability platform, can measure intrinsic fluorescence of proteins, can also deal with reporter dyes if your protein doesn't fluoresce or your buffer quenches the fluorescence, can be used for sizing and polydispersity as well because it has DLS. You can use it in thermal ramps and isothermal experiments, run up to 48 samples with a sample volume of 9 microliters required. Our solutions are built for biologics, and they will help you get the full scoop of delicious out of your ADC. And we can even add some sprinkles. With that, I will pause and see what questions have come in so far. Thank you very much.
Thank you for that very informative presentation, Andre. It is now time for our question and answer session. So if you have any further questions, please do send those in. You can submit these by typing into the question box to the right of your screen. So the first question that we have for you, Andre, is, can Uncle measure TM for oligos? If yes, how?
Thank you very much for this question. Uncle is able to measure fluorescence if the analyte is excitable at 266 nanometers or at 473 nanometers. So since oligos would absorb around 260, if the 266 excitation laser is appropriate, we should be able to follow the fluorescence emission of the oligo in the temperature gradient. If you were to use a dye, a reported dye for that, that works with 266 or most likely with 473, that should also work. So yes, I think in principle, Uncle can be used to monitor the melting of oligos as well, yes.
Lovely, thank you. The next one we have is, what is the volumes needed in the individual instruments mentioned today?
Thanks for the question. Let's go through the instruments in the order I presented them. So Stunner has a throughput of 96 samples in an SBS plate with 2 microliters of each sample. Then for our buffer exchange Unagi, we can run up to 8 samples and we can go down to a volume of 0.5 milliliters. So 8 milliliters to 0.5 for buffer exchange. If you need to go to smaller volumes of your end product, we have a second buffer exchange solution, which we call the big tuner, that can go down to lower volumes than 0.5. For the viscometer Honeybun, we have a volume requirement in default mode of 35 microliters. We have a low volume mode as well that can handle 15 microliters of sample. And in both cases, not all the sample is going to be pushed into the channel. So there is some that can be recovered as well. Throughput-wise, Honeybun can take up to 10 samples at a time. And then Uncle, our stability platform that I presented last, has a throughput of 48 samples, between 1 and 48 samples, and it needs 9 microliters per sample.
Lovely, thank you. We have an attendee asking here, what is needed to run these instruments?
You need, of course, the instrument itself. You need a computer, but we do provide the computers with the software installed with the instrument. So instrument, computer, software. Our software licenses are usually allowing up to 5 installations. So you could run it in the instrument computer itself, and then you can also analyze on your own laptop if you choose. And then, of course, you need the consumables. So that would be the Stunner plate to use Stunner. It would be the bun to use Honeybun. It would be the uni for Uncle. And if you use Unagi, you would need the Una. So our consumables are disposable, which is really good for multi-user facilities and to prevent cross-contamination. So your sample does not come into contact with the instrument other than in the consumable, which is an exchangeable consumable. So those would be required to run the instruments.
Lovely, thank you. The next one we have is, could Stunner be used for others than ADCs? For example, for seeing if antibodies coupled to beads or to fluorophores used for immunoassays, or even the antibodies alone are aggregated?
So let's take the first question for the first part of the question first. So can Stunner be used to find out if an antibody is bound to a bead? I think that's going to be a little bit more tricky because most beads, as far as I remember, don't have a pronounced absorption of their own. So Stunner being a UV vis photometer, if you can use the unmixed algorithm to take apart different analytes that fluoresce that absorb differently. Now beads usually don't do that. Unless they're labeled. So if they were labeled, it could potentially be set up like that. We could look at the size increase of the bead upon binding of the antibody. So could look at that with the DLS output of Stunner. So that could be a possibility. So with beads, things are always a little bit more complicated, but I think in principle it should work. And I will write back with more details on this question to the person who asked. Can you tell me the second part of the question, because I forgot? There was something about beads, and then there was a second part.
Yeah, of course. The second half of it was could they be used for or fluorophores used for immunoassays, or even the antibodies alone are aggregated?
Well, for aggregation, of course, Stunner offers DLS, just like Uncle does. So you can look at aggregation of antibodies of any protein, really, with the DLS signal, because you will be able to tell the hydrodynamic diameter and also the polydispersity index. So I think that's what you would want to use. And of course, you can use that with fluorophores as well. So protein plus fluorophore, and look at, is that hydrodynamic size increasing beyond what you would expect for a simple interaction, and indicate aggregation. So I think in general, the combination of UV-Vis and DLS in Stunner makes it broadly applicable to many protein applications. And I think the ones that were part of this question, they should all be handleable in Stunner, yes.
Lovely, thank you. The next question we have is, can these tools be used only for proteins?
No, they cannot. I mean, yes, they can be used for proteins, and they can be used for other analytes as well. So especially when it comes to viral vectors, so let's say AAV and adenovirus, Stunner can give us the titer of those and can also determine the full empty ratios. Uncle can be used to assess the stability of an AAV. We can basically look at how stable is the capsid shell of the AAV itself, and what temperature would it lose its payload. So the full spectrum fluorescence that we're recording in Uncle gives you access to using a reporter device like CyberGold, which we would use to look at the ejection of payload from the capsid. So the tools can definitely be used, and of course the buffer exchange as well, for viral vectors such as AAV and adenovirus. We can also work with nanoparticles. So we have some pilot data about LNP stability that we've measured in Uncle, and also looking at their sizes and size distributions in Stunner.
Beautiful. Thank you very much, Andre. Well, that's all we have time for today. I would like to thank again our expert speaker, Andre, for the informative presentation and discussion. And a big thank you to everyone joining us online. We hope you found this a worthwhile session. If you have any further questions, please feel free to email me at editor@selectscience.net, and I will follow up your questions for our speaker. Remember, you can download related resources in the tab to the left of your screen, and this includes the certificate of attendance. If you would like to listen again to today's webinar or invite a friend to listen to it, it will be available to watch on demand in just a few days. Goodbye, and thank you once again for joining us.